I plan on having solutions posted for the exam probably by the end of the day tomorrow. I'll just post it. You'll see all the solutions. I'll try to write some explanations for things along the way. It's because you are not going to get back your redos. Okay, you'll see there'll be a column in Canvas where I'll have redo, and it'll be so many points out of 0. The 0 is so that it doesn't add it to the class total. So it's the same thing as adding those missed points back to your exam. Right, at the end of the semester, I have a bucket of points, and I weigh that bucket of points. That's all. A point is a point is a point. So that's how that's going to work. That's why I asked you to keep copies of everything before you turned it in, so that you would have it, or of your answer sheet and your solutions and that kind of stuff. So, but I'm just not going to hand all that stuff back. So you'll see what you have by the end of the day tomorrow. You should be able to go in and look at all the solutions, and then I hope to have everything in Canvas by the end of the weekend, because we are getting close to midterm, and your interim grades will be based on whatever I have graded up to this point. So it's a snapshot in time. So the good news is about this is you still have plenty of opportunities to earn points at the end. And after thinking about it, I didn't put this in my syllabus, and I should have, but I'm going to just let you know this is kind of how I do my classes. Because the final exam is, even though it's just the last exam, it is comprehensive in a way because we've learned all this stuff. If you do better on the final exam than your overall class grade, I will give you the better grade, okay? So it is always possible for you in this class to do better up until you turn in your final exam. Okay? Does that make sense?
Yeah, that makes sense.
Does that sound fair? Mm-hmm. All right. Because I want you to learn this material. Okay? So we started talking last time about, in Chapter 6, this idea of stereogenic centers. We introduced that. We started talking about R and S. We know that we have to look down the carbon lowest priority group bond, right? So if that's this, I'm holding the lowest priority group in my hand, I'm turning it away from me, and then I'm looking to see how the 3 substituents move. If it goes 1, 2, 3 in a right-handed direction, like turning my car wheel to the right, it is R. And that's the easiest way to remember. R is right? And if it goes the opposite way, that's to the left, that's S, which means sinister, okay? Don't worry about that. You don't need to know it. But anyway, that's how you do it. You have to be able to assign priorities, and we talked a little bit about that, okay? Now, I don't think we got to this slide, right? All right, this is why this is important. And I think I did talk a little bit about why it was important last time. This is one of the reasons why many of your drugs are expensive, is because you have to be able to generate chiral centers in a variety of drugs because of just certain situations, right? So here's ibuprofen. This is Advil, right? This is probably what many of you take after class, right? It is an anti-inflammatory. It lowers fever. It helps headaches. It's an anti-inflammatory if you've got muscle pain, all that kind of stuff. Right? What are the functional groups? Carboxylic acid, right? We've got a chiral center, which isn't a functional group, but it's a chiral center. We've got this functional group that we're going to learn about later. It's called an aromatic ring. Okay, we'll talk a little bit about that, but it looks like a bunch of carbon-carbon double bonds, right? So you can kind of think of it like alkenes. But it's a special type of alkene that we'll learn about later. It doesn't do the type of chemistry that we've learned about so far. And then you've got this alkane piece that's hanging off the end of it, right? And it turns out that the S enantiomer of ibuprofen is what's responsible for the anti-inflammatory properties. The R enantiomer does not give anti-inflammatory properties. This molecule sits in what's called the cyclooxygenase enzyme active pocket. Cyclooxygenase takes arachidonic acid, oxidizes it, and makes what are called prostaglandins. Prostaglandins are responsible for inflammation, fever, and pain. This sits in the active site of that enzyme and keeps that from happening. That's why your fever goes down, your inflammation goes down, and your pain goes down. Okay? The R enantiomer can't fit into that pocket. It's like a right hand into a right glove is what the S enantiomer does. Right? So the enzyme looks like a right-handed glove. This looks like a right-handed molecule, and it fits. The other one doesn't. Okay? And so that's the case. Now, Advil is pretty cheap, right? You can go to Walmart, you can get it off the shelf. They sell that to you as a racemic mixture, meaning that it is equal parts R and S enantiomers. So if you take an 800 milligram ibuprofen, which is what I use, but there's a prescription, right? 800 milligrams, only 400 milligrams of that tablet is actually doing the work. What happens to the other 400 milligrams? My body excretes it. I'm wasting it. But they have been able to show over years that the R enantiomer causes no harm biologically. So it's just cheaper to make it as a racemic mixture and sell it. That's why it's so cheap. That is not the case if you use Aleve. Aleve is naproxen sodium. Okay? This is naproxen. Okay? Looks kind of similar in a lot of ways, right? It's got a carboxylic acid just like ibuprofen does. It's got a methyl group just like ibuprofen does, right? There's a methyl group there, there's a methyl group there, right? It's got a chiral center. Okay? Notice also the S enantiomer of naproxen is anti-inflammatory, but it's also got this bigger ring, right? So a lot more double bonds. This is called naproxen. This is the anti-inflammatory agent. If we sold that to you as a racemic mixture, we would kill you. Because the R-naproxen enantiomer is a potent liver toxin. Kill your liver, you're dead. Yeah. You all depend on some chemist being able to make only the S-naproxen to take this molecule. Okay? If you bought this from somebody that didn't know what they were doing and made an equal mixture of R and S, naproxen, you'd die. Eventually you would poison yourself and die, right? It matters because this will fit into an active site of something that kills your liver. Okay? So it's very, very important that we be able to make these molecules, figure out how to either make one hand or the other, or if the only thing we can do is make both of them, how do we separate them? How do we get the S away from the R? Okay, we have to be able to do that. Yeah.
Kind of slightly off topic, but is that why, like, kind of people who make like drugs, not like good drugs, like bad drugs, is that why they like some people like die of like poisonings and stuff like that because of like the chemistry of it? Because I watched this video on like something to do with like the war on something.
The war on drugs?
Yeah.
Yeah. So we'll actually have a slide on that here in just a second. We'll talk a little bit about that. And then our fluoxetine, you all might know this as Prozac. And it is the R enantiomer of Prozac that is actually the antidepressant. The other molecule doesn't help with depression at all. But I do believe, even though this is the enantiomer that is active, I do believe that when Prozac came out, it was originally sold as a racemic mixture, and I don't think that there's any harm in the R enantiomer or in the S enantiomer, excuse me. But I think Eli Lilly does sell it only as the R enantiomer as Prozac, so that they have a patent that they are able to protect through that way, and they're able to charge you more for that. That's the business side of medicine. So, these are just a few examples. Most people take some type of anti-inflammatory agent at some point in their life, and it's important. If you go and buy a bottle of Aleve, if you read the back of it, it will tell you that it is the S enantiomer. If you buy a bottle of Advil, it will just say contains ibuprofen. It doesn't say R or S. Okay, so again, very, very important. Now, getting to illicit drugs. This molecule is methamphetamine. Okay? How many people have ever watched Breaking Bad? Oh, yeah, good. It's a good show, right? It's been over for quite a while, but they've had a couple of spin-offs. One of my favorite series of all time. In fact, one of my college professors was a consultant for the show, and she posted a bunch of pictures with her and Bryan Cranston and all of them. It was kind of interesting and neat. So, just to let you all know, for those of you who've watched, methamphetamine is not blue. That was a thing just to make it kind of cool for the show. Methamphetamine is a very simple molecule. In fact, you see some similarities to ibuprofen, this ring. You see a chiral center. Where's the chiral center?
Where the substituent?
Yeah.
Right there.
Yeah.
Yeah, that is the chiral center. It has one chiral center. It is called methamphetamine. You see that there's an amine functional group. Okay? And that amine has one hydrogen attached to it. It has this chiral group attached to it, of course, or what has the chiral center, I should say, and then just a simple methyl group. That's why it's called methamphetamine. Okay? Very simple molecule, very easy to make. That's why there's a methamphetamine problem around the world, actually, but particularly in the United States, because just about anybody who knows how to mix a few things together can actually make it. We will not talk about that. However, the S enantiomer of methamphetamine is the active component of crystal meth, not the R enantiomer. Okay, so if we had crystal meth, it is the S enantiomer. So when someone, I'm not going to say you all, but when someone goes and buys crystal meth and they buy a gram, only 500 milligrams, or half of it, is what's given them their addiction. Okay? So somebody should really go and negotiate with the drug dealer, right? I only want to pay half because only half of it really works. Yeah.
You said crystal meth is the S enantiomer?
No, the active ingredient in crystal meth is the S enantiomer. Crystal meth, made the way that people who make illicit drugs make it, it's a racemic mixture. It's a mixture of R and S. However, many of us, myself included, have taken methamphetamine. Okay, I have taken the medical version of methamphetamine, which is the R enantiomer of methamphetamine. It's called Lev methamphetamine. Lev meaning levorotatory. We'll talk about that later. But it is the R enantiomer. If you go to any drugstore right now and you buy a Vicks Vapo inhaler, and you read the back of it, it will say it contains so many milligrams of Lev methamphetamine. Okay? This stuff, it opens up your airways and allows you to breathe better. Okay? So the people who are taking the illicit drug is actually a mixture of R and S. Half of it's getting them high. The other half is clearing their nostrils very well. Okay? So I'm not going to say they don't get some benefit from it, but it ain't worth what they're getting on the other side. Okay? So these two molecules actually are identical in every respect except how they function biologically. Right? This is like a left-handed glove. Your nostrils need that left-handed glove, that left-handed molecule to fit in their left-handed glove. This stuff does all the work in the brain that makes you high and go crazy. Yeah.
Are they, since they're the same molecule, are they made from the same things?
They are. They actually are made in a very. So there are companies across the world who make lead methamphetamine. But since this enantiomer is the illicit drug, you don't want to make that and then throw it away and worry about somebody getting it and selling it, right? So they have figured out ways to only make the R enantiomer. Okay, so they use chemistries that are special that only make the R enantiomer. Now, they could make both and separate them, right? Because just like I can separate, think about this. if I work on a glove assembly line and there's a mixture of right-handed and left-handed gloves coming down the assembly line, and I got to put the right-handed gloves in the right-handed box and the left-handed gloves in the left-handed box, can I separate them? I can. I can take my right hand and everything that fits, I just drop it into the right-handed box, right? Everything that fits my left hand goes into the left-handed box. So I can actually separate them. There are ways to do that with molecules as well, okay? And we're not going to go through a whole lot on that. But your book does talk about resolution of enantiomers at the end of chapter 6. And we're not going to spend a whole lot of time on it. But there are ways in which you can separate these enantiomers quite easily. Okay? They are enantiomers of one another. One helps clear your nostrils, the other gets you high. All right? And ruins your life. Okay? So, with that being said, we are going to finish chapter 6 today, but before we get started, I want you all to do some group assignments. So, you all need to break up into groups. Spend about 20 minutes grappling with these 4 problems. So groups of 3 to 4, something like that. You 4 can all just work together. Use your model kit. Somebody in the group should have a model kit.
What do y'all think? The CIP really. I guess when the lowest priority substitute is facing right, whatever. Like, I don't know if it's or not.
I was in like these life stars and they start on high school, and then they start like maybe like blue hydrogen priority goes
So the lowest priority is facing away
to
from
the
the observer.
what? Or like which way we go.
Molecules? Molecule? Wait, what do you mean?
Like like this whole group, what would you call this?
I think it's a molecule. Yeah.
Okay, that's a, oh, since, oh. they need, so, the TPO will say if there's two different, they need to be
There was,
so essentially what I'm reading is, if there's two different, if the answer is two different things, two different,
right,
they need to be its own different thing.
yeah, right, so, how would you describe CIP rules?
The CIP rules are the rules that are not, but again,
Whatever, so whatever. The lower, also, if the lower the active number, the higher the priority.
lower. Well, yeah, that's ability to just want to go on to the main idea, which is if you put
How do you put in yours?
I read it as the lowest priority input on the surgery center is facing away from the observer. So imagine if, I would say, let's just say Y1 is the lowest priority. That usually hydrogen not exists.
Well, I'm drawing it like this, and you don't know whether.
It's just hydrogen. And so with the lowest priority on the stereogenic center,
So I would show the molecule that you have to draw. On two, you all have to draw 4 molecules total. You have to draw the R and the S, enantiomers.
and then I say, if
I just showed you how things are connected, I didn't show you whether it was R or S.
all the remaining substituents rotate
You have to
clockwise,
use the solid wedges and the dash wedges
it is
for the groups.
all
I think it depends where you are.
molecule,
I'm trying to think about it. This is like I have mine bottom.
whereas
So when I got it,
So essentially what I'm saying is, we have to split it as well. If the priorities goes 1, 2, 3, or you have it 1, 2, 3, or is it 1, 2, 3, like the same direction. And it's clockwise.
so I read it as this one, so I'm just doing all.
But if it's 1, 2, 3, or is it 1, 2, 3, or is it 1, 2, 3, that's it's a long sentence, but that,
Depending on the location of the elements,
I would say atoms instead of elements.
and then it could essentially be RS.
So Chiron is the stereogen.
Do I go one towards you or away from you?
Glad that's not, glad that's not.
So whenever the molecules.
Bromine,
So draw,
holding the methyl.
no, wait.
Fluorine comes from bromine.
Oh, Sarah.
So,
Oh, right. So bromine would be here, and the fluorine, then, so I think it's going. Do you have a log?
draw name.
No.
Let me just put this back.
Don't be afraid to put them on. Now, you don't have to use, in your model kit, you don't have to use all the atoms. You can say that this group is a certain color.
It's
Just need to have
FCL
one color
chloride,
for
that's
the,
the order.
and you can just assign a different color.
FCL chloride.
So 40 kind of green, for example, methyl could be blue, whatever you want to do.
Now, for number
You can
two.
just hold the most priority group.
Oh.
One, two.
I guess we can draw the dash line.
You got to draw the wedges and the dashes. Whatever the chiral center is, you're gonna have groups that are in the
It
plane
doesn't
of the
matter
paper.
which one is on it.
Out of the plane of the paper, something goes behind the plane. So you want the chiral carbon itself to be in the plane of the paper. Two groups still in the plane and two groups working out.
And so the carbon change relatively, it's in one plane.
Oh, so it's backwards.
But I don't draw any wedges or dashes. So you don't know if that's just.
How do I get
showing
this?
things you can use. So you have to determine what's coming out.
It really doesn't matter which one. It's just the point. It's just the perspective where you see it. So it doesn't matter which one you want to make solid or dash. But the energy reservoir should be
Well,
the other.
you know you gotta do it in place, you gotta do both the R and the S.
Well, the whole molecule does. So it will be just like.
So it would be like this.
The dash is below the plane of the paper. Solid wedge is coming out of the plane. And everything else is in the plane.
Wait, what? I'm confused.
Oh, second. Oh, my God. Where? Well, if it's like he says, but you might bring up the purple.
I think this one does.
I'm also. I see an example of that. No, oh, never mind. The solid dash actually does not swap. So it's essentially, you're drawing it as a mirror molecule, but the dash is. Yeah.
Oh, I guess it's where the, is it where the legend plays Don't ask me. So, for these stereo centers, where the.
Let's yeah.
It's the carbon that has the 4 different things attached to it, right? Yes, so you got the chiral center marked right.
Okay. Yep, and then.
And this one, this is in the plane of the paper, this is in the plane of the paper, that's behind, this is coming out. Here, this is coming out, that's going back, that's in the plane of the paper.
So how do you get the priorities again? So it'd be like.
The paper is behind.
I don't think you can do that, that's for easy.
And the easiest thing when you're building models, if you only have one stereo center, is to just use your 4 colored spheres.
I don't know.
So just assign the groups a color, and then you can,
Oh, okay.
it's just quicker to put together that way.
It's the same thing, just different.
What you doing, Dakota?
A car on the fair.
Okay.
Oh.
We want to,
Wait, is flooring still more priority?
bromine is more priority.
So,
I'll give you about 10 more minutes. Then we'll go over.
No.
Like a socket is right.
Or
Oh.
These are chiral. So I know just like, so I kind of figure that out.
so,
You're going counterclockwise, so
So,
I don't know if
you cannot look at this two times.
wait,
That's the origin that you were looking at from. Let me go to because we have the
when you're assigning.
most priority of the way in the server. Imagine and this solid wedge is going.
Oh, I did spell it that way.
Draw the other one?
so this should be,
Well, you drew the other one by simply solving the ancient method. It is one.
Oh no, the lowest one should be away.
But now the lowest part of your facing, so when you make the assignment, you have to know the
Well,
it needs to be turned.
yeah, I can tell that you're holding it towards you, but from your point of view, that lowest
But
priority
if
is
the,
away.
if the top one is truly S, then the other one would be truly R. It just might look like it's S.
no,
So the thing about the lowest priority group, the example that I used on Monday was Big Ben. Clark. You're looking at Big Ben, like you should look at Big Ben.
Imagine this one,
Clockwise,
the lowest
right?
priority, you know, what you
The
hold.
hands are moving in the clockwise direction. If you were inside Big Ben looking out.
was, he totally
it would look
was,
like
it was a
it's
great-
counterclockwise.
This,
I think it was like this.
this means.
I'm pretty sure.
The solid wedge means that it's coming towards you. Coming out of the plane.
deep breath,
Towards
deep
you,
breath,
the
it's gonna
observer.
be okay, deep
The
breath.
dash wedge means it's going below the plane of the paper, away from the observer.
You got this.
You're on the right track.
I mean,
Outside of the plane, this is the plane.
no.
Yellow is outside, black. Yellow's in the back. Then the red, and
Yeah, that's, I understand how I can.
those are the colors that.
So if it was from your point of view, it would be like this.
From my point of view, it would be like that. I'm
Okay.
holding the lowest priority group away from me, and I'm looking down that carbon lowest priority group line. And then if this was high, second highest, third highest, it would be on. If it was highest,
Yeah.
second highest, third highest, it would be.
Okay, now let's make the, yeah, so now we just flip it. See, choose the outside.
Well, think of it, so if I'm holding the lowest priority group, and if I go from highest priority to lowest priority, if my fingers are moving clockwise back.
would be a higher.
I mean, it could be 1, 2, 3, that's still a clockwise fashion.
So I'm not.
Got it.
That's right. So you assign the priorities, you know that the lowest priority is away from you, and you just look at the 3 that are still on the card. And if it goes 1, 2, 3, and your fingers moving in the clockwise direction, it's on.
Instead of looking
If you
at.
go 1, 2, 3.
Yeah,
and
yeah.
So what about like this side?
And that's parts of the.
I'll leave these.
There's only one Kairos center. One.
Well, I'm saying like the parts that are here, like they're all the same.
I can know this is.
They're all, but then we have to look at the next item to determine which one is.
We changed the.
Yeah, but you keep going up to. So we have hydrogen
Wouldn't
on
this
this
be,
card. So I know that has to be the lowest.
This should be
And
all.
I've got carbon,
yeah.
carbon, carbon, you're absolutely right.
So this is clockwise.
So that's gonna be my third
You
priority.
might want to.
I've got to decide between these two things.
By where the surgeon center is. Is that what? Okay.
But
So
they're all
wait,
gonna
so
be-
wait,
So if I look at this.
since this is in flip, we need this.
I know that this is a carbon, this is a carbon, this is.
Okay, you're right.
This carbon is only attached to
What I
iron.
recommend you to do is.
This carbon is attached to these two carbons. And this carbon is attached to this. So I know that this one has to be.
You know.
So now I gotta look at this. Carbon, carbon. This. What is attached to carbon? So this is attached to carbon. This is attached to a carbon.
And so,
So I can't make a decision. So I go out to the next one. What's attached to this carbon? Three hydrogens. And what's attached to this carbon? What's attached to this carbon? And? Carbon attached to carbon. So I feel. But this, I'm only talking about this carbon. So that carbon's attached to the carbon, with two hydrogens in it. So when I look at this carbon versus this carbon, this one wins. So this group is the hydrogen. This will be one. This group is that make sense?
I put for the rules I have, like, you know, location of the atom, it's the overall as, and there, what is it?
We'll work through them. Get on to the, we've got just a couple more minutes. Let's get on some of the other stuff. Yes.
Can we switch it? Outside in here, then it's here.
Oh. I think I'm gonna do.
You also messed up your bonds.
Yeah, well, this bond, I switched this bond, so this wasn't that, we put the opposite, so we had.
Oh.
And then
Yeah, I'm agreed to a category 5.
So I just, that's absolutely.
okay, how is this at zero? This is what I thought
Because
was
what
very.
point is up.
I can understand that you said that.
I don't know where y'all are gonna stay.
Got a question?
I just don't know how to
There's just some.
Right now, all you gotta do is draw both and answer those dashes and wedges and go back in.
You might not be.
So really, I just switch to the groups.
Oh, this is easy to do that. I think it's easy to decide. Don't you think so?
To get cut off if I know.
Oh, yeah.
I've identified the chiral centers before, we have to walk.
Yeah.
But it's okay. Made it harder.
If I look down, is it the hydrogen is naturally facing away from us on the Earth? Like, to me, I'm pretty confident that we would go this molecules.
All right, folks.
From our point of view.
Let's work through them. So, just to let you all know, questions similar to this will be on the test. Okay, so not these exact questions, but these are the types of things that you need to be able to grapple with and answer on an exam about stereochemistry. All right, so let's look at one. In your own words, describe the Kahn-Ingold, Prelog, or CIP rules.
Depending on the location of the atom, it could be R, S, and also depending on the stereocenter and what it's attached to.
Okay, that everything you said there is true, but what are the CIP rules? Selena.
Assign priority, and then lowest priority away from you. Determine if your rotation from highest to lowest is clockwise or anti-clockwise.
Okay, that's true too. What do you mean when we say assign priority?
The highest atomic number
Okay, how do we do that?
gets one.
We have to use the periodic table, right? All right, very good. So we have to be able to identify first the chiral center. We have to see what the groups are that are attached to it, and then we have to assign priorities to those groups. Okay? And we have to go out until we find a difference. So that's what, something along those lines is what you should have had for question number 1, and everything that I heard was pretty good. So question 2 was draw and name both the R and S enantiomers of the following molecules. All I gave you was the molecule and how it was connected. I didn't tell you anything about stereochemistry. So the first one, I just put Br and F on carbon number 2, right? You don't know what's coming out of the plane. You don't know what's going behind the plane. I drew everything in the plane. I'm just showing you how things are connected. And you have to come up with the dashes and the wedges, right? So the easy thing, since you have to do both of them, the easiest thing to do is just to leave all the carbon atoms in this chain in the plane of the board. Make one of these substituents come out towards you and one of them go away from you, right? So you can have something like this. So you tell me which one do you want coming out towards you first?
BR.
All right, let's put bromine out. And that means that fluorine's going away from us, right? So now what we have to do is we have to assign the priorities based on the Kahn, Ingold, and Prelog rules, right? I've got bromine, I've got fluorine, I've got carbon, and I've got carbon. What's going to be number 1? Bromine. Why bromine and not fluorine? Higher atomic number, right? So I know that this is going to be number 1. I know that fluorine beats carbon, right? So I can assign number 2. Now I've got to assign 3 and 4. Both of these are carbon. So I can't make a distinction on that first atom. So the easiest way to keep track of this is to just do some simple accounting. Draw parentheses. What's attached to this carbon atom? 3 hydrogens. Put 3 hydrogens in those parentheses. What's attached to this carbon atom?
2 carbon atoms.
No. Remember, we go out from, we don't consider, we've got 1 carbon atom and what else?
2 hydrogen.
And 2 hydrogens. So we've got a carbon and 2 hydrogens. And always list in those parentheses in order of increase, starting with the highest priority atom and going down. Carbon beats hydrogen, right? So now look in the parentheses. Which one wins? Carbon beats hydrogen every time, right? If I couldn't have made a distinction there, I would have gone to the next atom. And if I go through all those atoms and I can't make a distinction, then I have to go on to the next atom. Okay? And that can go on for a long time. But, so now we know which one is number 3. Which one's number 3?
DC.
This one, right? And so my methyl group is priority number 4. So, Dakota, let me see your model kit.
People.
Yeah, you got one already. I need some other colors. Since I'm only dealing with one stereo center, I just need one carbon atom. All right, and so I'm going to define what these different groups are. I'm going to make bromine red. I'm going to make fluorine green. I'm going to make methyl white. And what other color do I got? Blue. And so I'm going to make my third one blue. All right? So, there's my methyl group. It's white. It's in the plane of the board. So white, the stereo center's in the plane of the board. And then my blue is also in the plane of the board. So I'm going to put my blue right there. Okay, does everybody see that? This is going away from me, isn't it? It's going behind the plane of the board if we imagine it right? So what color do I put back here?
Fluorine, green.
Green. And then coming out of the plane of the board towards me is bromine red, right?
Yeah.
All right. So now I've got it exactly like it is there. This is the plane of the board. That's right. There's my stereo center. That's going away from me as fluorine. This is coming towards me as bromine. I grab the number 4 priority group and I turn it away from myself. And so I red, green, red, green, and blue, right? 1, 2, and 3. So I'm going in what direction?
S?
Red, green, blue.
Right.
I'm going R, right? So this is the R enantiomer. Now how would you name this molecule? R, and R needs to be on italics. I can't draw italics very well, so it's R, what? Give me everything.
Dash.
R dash 2
dash
bromo
dash
dash 2
dash fluoro.
To make sense? So now what do I need to do to get the S enantiomer?
Just draw the mirror version.
All I have to do is switch 2 groups.
Oh, okay.
If you switch more than 2 groups, you'll screw it up every time. So which 2 groups am I going to switch?
The F and BR.
I can switch the F and the Br. So now I've got fluorine coming towards me, bromine going back. I have just drawn the S enantiomer. So I just said all we had to do was switch 2 groups, right? So if I swap this group and this group,
One will be on the other side.
now I have this, right? And I hold it away, I can see that it is going in the S direction. I'm having to turn it to the, making a left-hand turn, Clyde, right? That's what I'm doing. Okay? That's the easiest way to do it. What else could I have swapped? I could have left this, the bromine, coming towards me. I could have had the fluorine still going away from me. But now, I swapped those 2 groups.
It's double bromine.
Oh, you're right. That is the same. I can switch any 2 groups and end up with the enantiomer. Okay? I saw a lot of you trying to do this in your head.
Don't do that, that's not helpful.
That is not helpful. You're not far enough along in being able to see 3 dimensions yet. Some of you are better than others, and that's okay. Some of you are more artistic than others, right? You can work that way. Build a model. You don't have to build the whole molecule. That's why we have different color spheres. Okay? Different color marshmallows if you're doing that. Okay? However it works for you. Okay. The next molecule first thing we've got to do is identify the chiral center. Where's that at?
The intersection.
It's right there, isn't it? Notice the hydrogen is not shown, but we know it's there.
Yeah.
So that's the chiral center, or stereogenic center, the chiral carbon, whatever you want to call it. Okay, so we have to draw both the R and the S enantiomers. Right? So we can draw that by showing that CH2CH3, CH2CH3, and I can swap any two groups, right? So I'm going to leave this coming out, that going back. Okay, just like we had before, but now I'm going to put, there's my one carbon, and I'm going to put the 3 there. These are now the R and the S enantiomers are drawn. This is the lowest priority group. It's 4. I've got carbon, carbon, carbon. I can't make a decision, right?
Yeah.
So I got to ask myself what's attached. What's attached to this carbon?
3 hydrogens.
3 hydrogens. What's attached to this carbon? Another carbon and 2 hydrogens, right? What's attached to this carbon?
Another carbon and 2 hydrogens.
Another carbon and 2 hydrogens. I can make a decision.
Yeah.
This has to be my lower priority group, right? So this is going to be number 3. Because carbon beats hydrogen every time. So I know that these two groups have to be higher priority than my methyl.
Yeah.
Right? Now I've got to make a decision here. Carbon, same as carbon. Hydrogen, same as hydrogen. Hydrogen, same as hydrogen. I can't make a decision yet. So what do? I go to the next carbon.
Here's what I found.
Yeah, good for you. What's attached to that carbon?
3 hydrogens.
3 hydrogens. What's attached to that carbon? A carbon and 2 hydrogens. Carbon beats hydrogen, so this has to be which group? That has to be number 1. That has to be number 2. Okay. Then you can go through and you can name them. So, what are going to be the names for these? One of them is going to be R dash what? What's the parent?
Hexane.
1, 2, 3, 4, 1, 2, 3, 4, 5, 6, right? So it's going to be a hexane parent. So we're going to have R what?
3 methyl hexane.
3 methyl hexane. And we will also have S, 3 methyl hexane.
So the one that we just numbered, that's F, right?
This one would be, so if the hydrogen's away, then I would have 1, 2, 3. That's going in the S direction. Yeah, so this one is that one. The other one is R.
Can you count as you like the one on the left? It's going to the left, so it would be S because it's going to the most.
Yeah. So if I think of this as my groups, right? So let's do this. My lowest priority is going to be, I'm going to call that white. I'm going to make number 3 blue. I'm going to make number 1 red, and I'm going to make number 2 green, okay? So that's how I'm going to keep track of it. So here's my chiral center right here, right? My white is going away from me, so that's number 4. All right, and then I'm going to have my red down here. It's going to be in the plane of the board. My blue is also going to be in the plane of the board. Everybody see that? This, and this are all on the plane of the board. Blue, the chiral carbon in red, and then my green is coming towards me, right? So now when I'm holding this, I go 1, 2, 3. It's like I'm turning it to the left. And that's why it's S. Okay? When you all watch me do this on the board, it makes sense, it looks easy. When you have to do it, ain't so much, right? You got to kind of struggle through it. It's not hard, but you have to follow the rules, and you have to not confuse yourself. And when you don't build a model, if you swap the angle of a bond, which is what I think you all did, Selena, in this, I think you drew the flooring going down as opposed to going up. You actually, what you really did was swap two group. You swapped a group and then swapped the other group. And when you did that, you ended up with the same molecule you started with, right? So that was a good lesson. It's very important that you keep track of everything. Okay. Question number 3. I gave you some biomolecules, cysteine and alanine. Anybody know what those are?
Huh?
Cysteine and alanine. You all have had some biology so far, yeah? What's cysteine and alanine? These are amino acids, right? What are amino acids useful for?
Protein.
Proteins, that's right. This is what you have to have amino acids to make proteins, which are the functional molecules of biology. So this was cysteine. That I gave you. Right? And I called it L-cysteine. You don't need to worry about that nomenclature yet, but I wanted to introduce it to you because in amino acids they call them, instead of R and S, they call them D and L. And you'll learn about that in biochem. Okay? D and L are not absolutes in stereochemistry like R and S is. Okay? It's very important to know. A D can be either R or S. But you'll learn about this in biochem. Why biochemists do things complicated is beyond me, but they do. Okay? So, we know where the chiral center is. Now we need to assign the priorities. Right? I've got carbon, I've got hydrogen, I've got nitrogen, and I've got carbon. What's number 1?
Nitrogen.
Nitrogen comes before carbon, right? All right. What's number 4?
Hydrogen.
Hydrogen. Now I got to decide between these two carbons. How do I do that? I ask myself what's attached to them. All right, so for this carbon, what's attached to it?
CO.
Well, the C is already.
Oh.
Yeah, it's just O.
Is it? It is not.
There's a C and then
It is OOO.
Oh.
Oh. Why?
Because
It's got a bond to a carb or to an oxygen. It's got a bond to an oxygen. It's got another bond to an oxygen. So it's 3 O's.
Wait, say that again? Where's the,
That's okay.
say that again, where's?
Okay, I got to ask myself what's attached to that oxygen or to that carbon, right? It's attached to an oxygen. It's attached to an oxygen, and it's attached to an oxygen. The carbon-oxygen double bond is the same thing as being bound to 2 different oxygens. For the Kahn-Ingold-Prelog rules. Yeah.
So when you determine the priorities, you never, put the carbons in it.
No, I'm asking myself what's attached to it.
Yeah,
That's right.
I answered.
That's right. So I'm asking myself what's attached to it. Okay? Now, what's attached to this carbon?
Carbon,
No.
Sulfur.
Remember, we don't count the chiral center.
Sulfur and 2 hydrogens.
Sulfur and 2 hydrogens. What wins?
The
Sulfur.
Sulfur wins,
Get the first.
right? Sulfur beats oxygen. So this is going to be the second priority group. This is going to be the third priority group. You look in the parentheses and you find a difference. Oxygen is different than sulfur. Sulfur is higher atomic number. It wins.
Wait, sir, why?
Here's what I found.
What do you mean you don't count the chiral center? Are there two centers here?
No, there's just one chiral center.
Yeah, so it's attached to, oh, never mind.
So I didn't count it in what's attached to this.
Oh, okay.
Does that make sense? Okay. So it goes 1, 2, 3. The fourth group is away from me, so this must be what? R. Cysteine, natural L-cysteine, is actually the R stereochemistry. All other L amino acids, you'll learn about this in biochemistry,
It's gonna be S.
are S.
That's confusing.
But it has to do with the fact that sulfur takes priority. Okay? Remember, R and S is about how we can systematically place the atoms three-dimensionally in space. Now, if I look at D-alanine, all right, let's go through the exercise again. What is the fourth group? Hydrogen. That's an easy one, right? What's the number one group? The nitrogen. Now, I've got to decide on these two carbons, which one's going to win?
The one with the oxygen?
The one with the oxygen. All this one has is hydrogens attached to it, right? So this is going to be my number 2 group. This is going to be my number 3 group, right? And so now I've got to turn that lowest priority group away from me, don't I? Right? So if I make this white, I make this, what did I make that there?
So there was something in the book about if the hydrogen is said to be in the front, then count them and make it the opposite.
You can, but you can mess yourself up doing that sometimes. Okay? It's easiest just to build a model. So red or white is going to be my hydrogen. Okay, so that's going to be coming out towards me. So I'm going to make, let's see, let's do it this way. So there's that. So this is going to be green. This is going to be blue, right? White is my hydrogen, and then so this is going to be my red, right? Okay, so now when I take the white group and I turn it away from me, I see red is number 1, blue is now number 2, green, so that is R. Right?
It's as if you're looking at the other side from the other side.
I'm looking at bin from the inside.
Yeah.
That's right. It looks like it's going S.
Like the big trend.
Yeah, it looks like it's going counterclockwise. But in fact, when I turn it around, I know it's going clockwise. And it turns out that all D amino acids, right, so this is D-alanine, have the R stereochemistry except for cysteine. D-cysteine is actually S because sulfur has this high priority. Okay? Does that make sense? Yes, ma'am.
I heard you say this like throwaway sentence just like real quick ago. You said since, like referring to the previous one, you said since this hydrogen is drawn away from us.
No, it's drawn towards us.
Yeah, what the other one? You said, it was just a throwaway sentence, I don't know if it was just whatever, but you said since it's drawn away from us, we know it to be R.
Well, it's drawn away from us, and I know that if I count, right, I'm looking down this bond, right? If I'm looking down this bond, it still goes in the R direction.
Yeah, I was just wondering, because like, it sounded like a blank statement, and I didn't know if you were saying that.
When the lowest priority group is away from you, if they go in a clockwise direction, you know it has to be R.
Okay, so like.
If it's going in an S direction, you know it has to be,
Because I heard that, and I was like, oh, it says something else.
yeah.
Can you explain how Devlin is R?
It is R because the groups are going to the right. When I built the model, right, the hydrogen was coming towards me, right? The nitrogen was going, let's see, how did I do that? There we go. So the nitrogen, well, there we go. So the nitrogen was red, the hydrogen is white, the methyl group is green, and the carboxylic acid is blue. And so when I grab the hydrogen and turn it away from me, I go, red is 1, right? Blue is 2, and green is 3. So I'm going in a clockwise direction, so that has to be R. But if I did it here, right, it would look like it's going 1, 2, 3. It would look like it's going counterclockwise, but it's the lowest party group, so it has to be going the opposite direction.
That's why we need a model.
That's why you need a model. I can do this in my head. But when I was in your boat, I couldn't do it in my head. And I've got 30 years on you, so, yeah.
Okay, so what if you don't have a model? Like, how would you do this? Because I can't get a model. So like, and every time I thought, oh, I have a little trick going on here, I can do it, and then I can't do it.
I'd buy a bag of colored marshmallows and some.
Could I use that on the exam?
I don't care. Yeah. Bring some toothpicks and marshmallows.
I'll do that.
Have a snack while you're doing it. I don't care.
I'll do this. Don't tell me to do it.
You can do it. You can do it. You can do it. All right, let's move on to the last one. So we've got, now this one I did draw in some stereochemistry, right? So these atoms are in the plane. I've got a hydrogen on this carbon coming out towards me, an OH going behind me. On this carbon, I've got the OH coming towards me, and I've got the hydrogen going away from me. How many stereocenters does this molecule have?
2.
It's got 2.
One there, one there.
That's right, it has 2. And from your book, you learned that the maximum number of possible stereoisomers is 2 to the n, is the maximum number of possible stereoisomers. So what is n here? N is 2. So 2 squared is?
4.
There are 4 possible, or let me rephrase that. There is a maximum possible number of 4 stereoisomers. There can be fewer, but there's a maximum number of 4. How do we get 2 to the n?
Well,
What can this stereocenter be?
R and R, R and S.
That's right. Each one of these can just be R or S. That's where the 2 comes from. N comes from the number of them that we have, right? So that's the maximum possible. And what Jason said, theoretically we can have RR, we can have RS, we can have SR, and we can have SS. Okay? That's the theoretical possible combinations. So is this molecule chiral or achiral?
I was trying to figure that out.
Oh, yeah, trying to figure that out.
I was trying to see if I could quote it. If it could be chiral is when it's non-super.
Chiral is non-superimposable on its mirror image. That is true. What was one of the little things we talked about last time? If a molecule has one and only one stereocenter, it must be chiral.
Right.
But since this has 2, it's not.
It may
Or
or may
may
not be.
or may not be chiral. Right? So you all are saying chiral final answer? All right. Turns out you're wrong. This one is an achiral molecule. It's called a meso compound.
I get it wrong so many times.
That's all right.
You walk so we can run.
Yeah,
So the ones that we just drew out before this, those would have to be chiral.
they are. They only have one stereocenter. Yeah. So,
Why is it no?
well, give me a few more carbons.
This is
Give me another carbon. We're gonna draw now. We're gonna build it out. I need a couple of white. I need another atom. Half atom.
Oh, half atom?
Yeah. Half atom.
I need some whites.
I need 2 whites. I need 1 more. All right.
You didn't rock that.
It's like you're the
So-
owner of the restaurant and the server.
White will be hydrogen, and the OH group will be red. So there's my 4 atoms in the plane of the board. You all agree with that? There's that methyl group. There's that number 2 carbon. There's the number 3 carbon. There's the number 4 carbon. So on carbon number 2, as I'm going to call it, I've got the OH coming out of the plane of the board towards me. So that's that, right? And the hydrogen going away from me. So I'm going to put that going away from me. Okay, everybody agree with that?
Yeah.
Here I've got what coming towards me.
Hydrogen.
So that's white coming towards me. And that is hydrogen, or oxygen, excuse me, going away from me. So everybody agrees that I built the right thing.
Yep.
All right. So, the hydrogen's away from me. Oxygen is clearly going to be number 1.
Yeah.
This carbon is clearly going to beat that carbon. So that's going in what direction?
R.
That's R. So the carbon number 2 has the R stereochemistry. Now let me grab the hydrogen on this one and turn it away from me, and it goes in the
S.
S. Now if you look at these groups, this carbon is exactly attached to the same 4 things that this group is attached to, right?
Oh.
So now if I rotate, I can rotate around carbon-carbon single bonds. Does everybody agree?
Yeah.
What can't a chiral molecule have? It cannot have a plane of symmetry. Notice there's a plane of symmetry that cuts this molecule exactly in half. So, if you built the molecule where this carbon is S and this one is R, we would be able to find that they are perfectly superimposable on one another because of this mirror plane of symmetry. Now, what happens if I swap these 2 groups?
R and R, it won't.
R and R is chiral,
Yeah.
right? So I can have RR, RS, and then the meso compound. So there's really only 3 stereoisomers for this molecule, but the maximum number of possible is 4. Okay? This is as complicated as it would be on an exam for multiple stereosymbols in terms of identifying the chirality. I could give you something that has a lot of stereocenters and ask you what's the maximum number. All you got to use is the formula, right? All right, we've only got 1 minute left. You all need to turn in a quiz for chapter 5. Turn in question number 519, A through C. Please leave it on the desk over there by Selena on the way out.